right, so we're going to be starting with 9.4 arithmetic sequences. I got a video from that excited British guy. I got to turn off my mic though to play it.
Possibly one of the greatest mathematicians of the last few hundred years. He really is a really large figure. Now, the story goes that when he was 9, he started to attend at school his arithmetic class. Now, arithmetic class would include lots of boys all the way up to the age of 15. Imagine, like, this is 1780 we're talking about, a long time ago. Imagine it's a drab schoolroom, worn, and the floor was uneven, and the teacher was also drab and worn and uneven himself. Apparently he was quite a bully. He would walk around with his cane and he would thrash the boys. Now, one day, to keep them quiet, this will keep them quiet for an hour, he gave them a problem to add up all the numbers from 1 to 100. So add up all the numbers to 1 to 100. So 1 plus 2 plus 3 plus 4 plus, and all the way up to 100. Right, that was the problem he gave the pupils, and they had to write on slate in those days. And when you got the solution, you would put your slate on the teacher's table. Now Gauss, when he was given this problem, immediately threw his slate onto the teacher's table with an answer. Now the other boys continued their work, adding up all the numbers, multiplying and adding and subtracting whatever they had to do. The brute of a teacher strolled around the classroom, throwing just pitying looks at poor old Gauss, just guessing the answer and throwing it onto the table. When the hour was over, he took the stack of slates, turned them over so that Gauss's answer was on the top, and read out the answer. To his astonishment, he got the answer right. The answer was 5,050, which meant that Gauss was able to solve it in seconds. How did he solve it? Well, he had a trick. The trick was, he noticed that if you add the numbers in pairs, I'm going to start with 1, and I'm going to add it to 100. What you get is 101. Now, if you take the second number and add it to the second to last number, 99, you get 101. You take 3 and add it to 98, you get 101. In fact, each pair that you make in this way would equal 101. How many pairs do you make? Well, there's 100 there, 50 pairs you make. So you just took 101 and times it by 50, and you got 5,050. So this story was...
All right, so that's kind of like a story about Gauss. He was a really well-known mathematician. If you ever study like upper-level math classes, you'll hear about Gauss, and different formulas and different things are named after him. He's just a big figure in mathematics. So this is a story. I mean, it's kind of one of those fable tales. Who knows if it actually happened exactly like it's been told, but it's one of those stories that have been told over and over to kind of demonstrate that sometimes hard-looking problems can have clever kind of solutions. So we're going to see notes for 9.4. Let me share my iPad. Okay. All right, so you guys see this right now?
Yeah.
Okay. All right, so looking at these notes, 9.4 arithmetic sequences, an arithmetic series. So we looked at sequences earlier this week. A series is just where you add up a list of numbers, while a sequence was just the list of the numbers themselves. So last week we looked at sequences. This week we'll be kind of finishing up looking at series where you basically find the sum of all the numbers in a list of numbers in a sequence. So example 1, which we just kind of solved the solution to in that YouTube video, to find the sum of a list of numbers, kind of the trick is you can look at what the pairs add up to instead of just adding each number individually. So that YouTube video, what Gauss noticed is that each pair, if you take the first number and the last number in the list, adds up to 101. And since there's 100 numbers, there would be 50 pairs. So 50 times 101 was 5,050. So that first example was kind of illustrated in that video. But so that's kind of the intuitive sense behind this, but there is kind of a formula we'll be using. But that really what the idea is when you're using this formula is you're figuring out how many pairs can you make and what will those pairs equal to. So that's kind of like the intuitive reasoning behind this. And this would work for any kind of problem similar to this we'll see. But for example, if you wanted to find out what the sum of the numbers between 1 and 1,000 is, or the sum of the numbers between 500 and 1,000, you could kind of use this same method. But let's move on. So finding finite sums. So we're looking at arithmetic. So if you look on the right here, this is our formula. The sum of a list of numbers is n over 2, and n is how many numbers you have in your list. A1 is the first number in your sequence, and AN would be the last number in your sequence. So let's look at an example. So example 2A, what is the sum of the arithmetic sequence where A1 equals 7, AN equals 79, and N is 8? So they're giving us all the information. We don't really have to develop it. So to find the sum, it would be the sum of 8 numbers. So n over 2, that would really be 4, times the sum of our first number plus the last number in our list. So if you work this out, or if you have a calculator handy, that would be 4 times 86. Let me pull up my calculator. So that would be 344. Work that out. You could either plug it in your calculator like it is, or if you want to simplify bits and pieces to kind of get there, it's up to you. Let's look at another one. So what's the sum of an arithmetic sequence where AN equals 80, N equals 11, and D equals 7? So what they're not giving us is they're not giving us A1. We have to figure out what A1 would be. So one trick you could use is use the arithmetic sequence from before. We could use this to calculate our A1, because that's what we're missing. So if you remember, the formula for an arithmetic sequence is this. So if we plug in what we do know, A of n is 80, or A1 we don't know. We know our n is 11, so that would really be 10 inside that parentheses times 7. So really what we have is 80 equals A1, sorry, I forgot the plus here, plus this would be 10 times 7, so that would be 70. So if we work this out, we'll really get A1 is 10. Another way you could do that, though, is if you know there's 11 numbers in your list, the last number is 80, the first number would be 10 spots in front of the 11th spot, so you could subtract 7 10 times from 80. So I mean, you don't really probably need to kind of plug it into that. That's what this formula is doing, but it might be more intuitive to do it without it. But now we know our A1, so now we can use this series formula, or arithmetic series formula. So now we would use, so S of 11, so the sum of these 11 numbers is going to be 10 over 2, because that's our n, and our first number we found in our sequence would have been 10, plus our last number they gave us was 80. So if you plug this in, this would be 5 times 90, or 450. So that's kind of the idea. We'll kind of see, I think there's, let's see what the next examples are. Yeah, we'll see like when they give you like a sequence, you'll be finding out what it is. But so sometimes they don't give you the information. You might have to do a little bit of work to kind of find either like your first term or your last term, or maybe your, well, you should know your n, but they have to kind of give you that one to be honest. But that's kind of the idea. But you just using this formula here. So I mean, once you get your information, just plug it in. But it's like that video we saw. Basically, you're thinking about how many pairs, oops, you can make. Erase this. All right, so if you, I don't know if you're looking at the notes, but on the other page, just some more examples, same idea. They give us a sequence, or it's a series, because notice it has plus signs, not like commas between the numbers. So we want to figure out this sum. So our A1 is 14. That's our first number. Our A of n is 116. Notice in this problem, they don't give you the n, which I just kind of said they had to, but they proved me wrong. But to find our n, we're going to have to use that arithmetic sequence formula. Or you could really notice the difference is 3. You could also figure out how many times would you have to add 3 to 14 to get the 116, but it might be harder. I mean, you could, I'll see if I'm right. I'll do it the proper way, and then I'll see. I think you could take the last term, 116, minus the first term, and then divide that by your d. So I think it's going to be, if I'm not wrong, it's 34, but let me do it the proper way. I'll plug it into that arithmetic sequence. But actually, let me just work it on paper real quick, because this is definitely easier. What I just did worked. Is it using the oh, maybe I'm wrong. Okay, I'm going to do it the proper way because I just had a little mistake. All right, sorry about that. So one way you can do this is use that sequence formula, which is, if you don't remember, it's A of n equals A1 plus n minus 1 times d. So our A of n from this problem is 116. That's your last term. Our A1 is 14. We don't know our n. And our d is, if you notice in this pattern, it's going up by 3. So your common difference is 3. So if you solve this, I'm running a little bit out of space. You would subtract the 14. You'll get 102. Sorry, this is going to be a little bit squeezed in here. If you divide the 3 over, you should get 34. And then you would just add the 1 over. You're going to get your n is 35 if you work that out. There it goes. So now you can plug this into that series formula. So remember, it's S of n, so S of 35, because we have 35 numbers we're finding the sum of. It would be n over 2 times A1 plus A over n. So that would be 14 plus 116. So if you plug this in your calculator, 35 over 2 is 17.5 times 14 plus 116, that would be 130. Let's see, so that I just got my answer is 2,275. That would be my final answer. If you don't want to do this part here, like where I plugged it in, one trick I just noticed is if you take the last term, 116 minus 114, you get the difference between them, it's 102. If you divide that by what it's adding by 3, and then add 1 to it. I mean, it's basically going through this process, but you could kind of memorize kind of like the arithmetic of what this process does if it looks scary to plug it into here. But basically, you take the last term minus the first term divided by the common difference, and then just add 1 to that result. That's kind of the thing you don't want to forget to do. Any questions so far? So
Yeah.
so
Yeah.
let's try this last one kind of together. I know it's been kind
What'd you say? No.
Just $1.
I do not have money for you.
All right. So looking at example D, what's our A1?
I'm doing this thing for school, Nick. Oh my goodness. 20.
What would our AN be?
That's the amount of numbers, right?
A of n is like the last term.
All right, 20. Negative 24.
Okay, do you know what the D is? What's like our common difference?
Negative 2.
Mm-hmm. And we're trying to find our n because we don't know. Because we need that, like in that formula, it's like the formula, remember, is S of n equals n over 2 times A1 plus A of n. So to figure out your n, you can use this sequence formula. So A of n is, from what we saw above, negative 24. A1 is 20. And then n, we don't know what it is. That's what we're finding. Times our D is 2. So basically we wanted to solve for n, so we could subtract the 20 over. So I'm running out of space. It'd be negative 44 equals n minus 1 times 2. So we're going to divide by 2. You would get negative 22 and add 1. It'd be negative 21. Sorry, I don't have space to like write that in, but you would divide the 2, and then you would add the 1 over. And now that we've got our info, these are the 3 we care about. If you look at that series formula, we just need the D to kind of help us get the N. We're going to do S of negative, or, well, what did I screw up? Oh, I forgot to put a negative 2 here. It doesn't matter, but like one thing I realized, you can't have a negative. Oh, it did screw up though. It would be 23. Because you can't have a negative list of numbers. That's why I was like, your N can't be negative. That doesn't make sense. So I'm sorry, it should actually be 23, because if you divide by negative 2, you get positive 22, and then add the 1 over, you should get 23. So I'm sorry about that. So now, because I kind of realized when I was writing this formula, I was like, wait a minute, you can't have a sum of a negative list of like a amount of numbers. Then it would be n over 2, so 23 over 2, times the first number plus the last number in our list.
Wait, what was the error?
My n should have been 23.
Mm-hmm.
And the reason I messed that up is when I was writing my formula down here, I plugged in a positive 2 and said this was supposed to be a negative 2.
Oh, okay.
That's what threw me off. I just copied it wrong from what we had above. Like I wrote
All right.
D. So I'm just going to plug this in my calculator, but it would be 23 over 2. So I'm just going to get, that's 11.5. And then times, well, 20 plus negative 24 would just be negative 4. So 11.5 times negative 4 is negative 46. So that would be like what this series would add up to. So just to kind of recap, because one, I made some mistakes, and this can be kind of tricky at first. Basically, all you're trying to do is, in this formula, you need to get your n, your A1, and your A of n. So remember, your n is how many numbers are in your list. A1 is your first term. A of n is your last term. So we saw an example A. It was nice. They gave me everything. I could just plug it in. But sometimes if they don't give you one of your terms, you need to use this arithmetic sequence formula and solve for whatever piece you're missing. So if you're missing your A1, solve for that. If you're missing your N, solve for that kind of thing. If you're missing your A of N, solve for that by plugging it into this formula here from last week. But once you've got all these pieces, just plug it into this top formula. So that's kind of the idea, even if sorry if it was kind of all over the place. The last thing we're going to look at today is something called summation notation. I don't know if you've ever seen this before. The sigma symbol, it's the Greek capital letter. Anytime you see this symbol, like it's this weird looking E, let's see if I can underline it, like this symbol here, that is sigma, and it means a sum. And you'll see this especially probably next year, or if you do end up in a calculus class for sure, you'll see something like this. But basically what it tells you to do is the sum of your function, this is the formula you're using, the bottom number tells you what number you start with. The top number tells you what number you're going up to. So basically what this would mean, like what this is telling you to do is you're plugging it into this function 3n. So we're going to plug in 1, so 3 times 1 plus, and we're going to go all the way up to 10. So we're plugging all the numbers between 1 and 10 into this function and adding them together. So plus 3 times 2, plus 3 times 3, plus 3 times 4. I'm already going to run out of space. I'll squeeze out make another row. Plus 3 times 6, plus 3 times 7, plus 3 times 8, plus 3 times 9, plus 3 times 10. And we're doing it the longhand. We'll see we can use that formula we did above, but for this first one, I figured I'd just write it out longhand, so just make sure you understand the notation. But if you add this up, just see, that would be, well, I might even just use this. Well, I'll do it. So 3 plus 6 plus 9 plus 12 plus 18 plus 18 plus 21 plus 4 plus 27 plus 30. Hopefully I didn't type anything. Nope, looks good. If you add this up, you get 165. But if you see this like sigma symbol, just know you're doing something, basically you're going to be adding a bunch of things together. That's what that sigma symbol represents, like a sum. Most of the time, like if you're reading this, you would say this is the sum of 3 of n between 1 and 10. That would be how I would read it. So let's look at some examples with this notation. It's going to be pretty similar to what we did above. We're still going to use that formula like S of n equals n over 2 times a1 plus a of n. So this first example, so we're using this, I'm just going to write well, here's the formula. This is the formula we're going to be using. So we need to find our n, our a1, and our a of n. So let's start by finding our first term. So we're taking the sum of 3n minus 8 between 1 and 40. So what would our first term be if we plug in 1? Because that's our lower limit. One thing, if you get into more advanced, they call this the lower limit on the bottom, and they call the number up top the upper limit. I mean, it's not that important, but I guess it might help you if you like hear that, to use that vocabulary. So to find our a1, you're just going to plug 1 into this function. So what do you get if you plug in 1 into this function? What do you get?
-5.
So our a1 is -5. To get your upper limit, you're going to plug in, to get your a of n or your last term, you're going to plug in the upper limit. So you're going to plug 40 into this function. So that would be 120 minus 8. So that'd be 112. So we found our first term, our last term. The last thing we need in this formula is we need our n. So to get your n, one thing you got to be careful about is it's between the numbers 1 to 40. How many numbers are between 1 and 40? And one common misconception, I don't know if you guys, does anyone, you guys have an answer? How many numbers are between 1 and 40?
Including 1 and 40.
Yeah. Yeah,
40.
and 40. Like, what are you thinking if you had to throw out a guess, if you don't mind?
39 and 40.
39 or 40, you're not sure?
Yeah, I'm not sure because I'm thinking about 0 and 40.
One misconception is a lot of times people will say it's 39. They just find the difference between them. But
Mhm.
since it includes the 1 and the 40, it's actually 40. Or
Alright.
if you just want to use this formula, like to find the number of terms, just take the upper minus the lower, so 40 minus 1, but you always got to add 1 to that difference. So you would just, your n is 40. And if you don't believe me, I'll just erase it. Like, let's say you want to find how many numbers are between 1 and 5. Well, let's say you thought it was 4. Well, you'd be wrong, because if you count it, it actually has 5 numbers. So you take the upper limit, 5 minus 1, plus 1, you'll see there's 5 numbers in that list. So one misconception, though, is just to take the difference. Be careful about that. But now that we have our info, we're just going to plug it into this formula. So it would be S of 40, because we have 40 numbers we're summing up. N over 2, so our n is 40, so that would really be 20, times our first term we found above was -5, plus our last term we found above was 112. So in other words, we'd have 20 times 107. So plug that in my calculator. Times 107. It is 2,140. Okay, let's look at another example or two with this notation. Was anyone, sorry, anyone still need this? Let's see.
No.
All right, this example B. So the first thing we want to do is you want to find those 3 pieces of information. So find your first term, find your last term, and then lastly, figure out how many terms are going to be in your series. So your first term, you're going to plug 1 into this function. So that would be 4 times 1 would be 4, plus 7 would be 11. To get the last term in your series, you'll plug in the upper limit. So you'd plug 50 into this function. So 50 times 4, that would be 200, plus 7, that would be 207. To get your n, you take your upper limit, so 50, minus your lower limit, 1, plus 1, so it would just be 50. Just one thing, well, we'll see in example C, but one thing to notice, that lower limit doesn't always have to be 1, but a lot of times it will be, because a lot of times you want to plug in numbers between 1 and something, or but it doesn't always have to be a lower limit of 1, just so you know. So now that we got our info, you just plug it into that formula. So S of 50, because we have 50 numbers we're adding up, equals n over 2. So 50 over 2 would be 25, times A1, so 11, plus our last term, 207. So really, this would be 25 times 218. 5 times 218. So 5,450. If you add up all these numbers. Okay. And then just one more example. Let's just kind of go through this same process. So find your first term, find your last term, find your n. So Nyla or Ava, what would our first term be?
So that's when you take like the lower part and you plug it in?
Yes. So yeah, good call. So like this one, you're not going to plug in 1, you're actually going to plug in 4.
Mm-hmm.
So what
All
would our
right, so
first?
that'd be -8.
Exactly. And I almost made a mistake. I'm actually glad I asked you to do that because I was about to plug in 1 out of habit, but pay attention to what your lower limit is. So yes, it would be -8. I almost wrote -2, like that would have been bad. But good. Upper limit to get your
-24.
so it would be -24. So because you plug in 12 into -2n. Then n, take your upper limit minus your lower limit and add 1. The reason you add that 1 is it's just because you include 4 and 12, like the numbers you're plugging in. So that's, you got to account for that kind of duplicate and take the difference. So it would be 9. So plug it into that formula. So S of 9, because we have 9 numbers we're really summing together, equals 9/2 times our first number plus our last number. Oh, no. All right, so it'd be 9/2, so that'd be 4.5 times -8 plus -24 is -32. So that would be negative, so it actually works out pretty nice. That'd be -144.
What a perfect number.
It always makes me like, I mean, it should always equal like a nice number depending on your function, but especially like 2, like if you look at like -2 times n, like you're only going to get a whole number if you're plugging in like integers between 1 and 12.
Mm-hmm.
I always get nervous when I have like 9 halves, like it's going to be a decimal to start, but they should work nice depending on what your functions look like. And then just some vocabulary review. Honestly, do I really care about these vocabulary? Not really, to be honest with you. I mean, the really, I mean, don't, I mean, if you want me to do it, I'll do it. But I mean, really, the thing I want you to take out of what we've done these past weeks is just like a sequence is just a list of numbers, while a series is like you're adding together a list of numbers. So that's really the key difference. So, and then like we saw last week, like it's the same thing with series. An arithmetic series or sequence is when you have like you're adding or subtracting something between them, while a geometric sequence or series is where you're multiplying, or even I guess you could think of it as dividing by a common number between each term. So an arithmetic series is the sum of, well, a series is just the sum of the terms. An arithmetic series, a series whose term would be that, I guess. Finite, it's basically a series that doesn't go on forever, infinite. And then limits, like the upper and lower limits. To be honest, I mean, it's not that, most of the, I mean, you know what finite is, you know what infinite is. Limits are what we kind of talked about above. Okay, so let me stop the recording. How do I do that?